This video is all about how to calculate upstream pressures and pipe sizing. Now, a 100-mile long pipe natural gas consists of several injections and deliveries. The pipeline is MPS 18, 0.375-inch wall thickness and has an inlet volume of 150 million standard cubic feet per day. At point B, milepost 250 and C, milepost 70, 60 million standard cubic feet per day and 50 million standard cubic feet respectively are delivered. So now let's begin to input this. Now they said from, let's say this is A, this is C or B, and they get to C2. This is our C. Now you see that at B, which is my post 250, my post 25 has a delivery, and C, which is my post 70, has a delivery flow rate of 60 million standard cubic feet a day and 50 million standard cubic feet respectively. So that means at B there is a delivery of 60 million standard cubic feet a day. Now at C there is 50 million standard cubic feet per day. Now the one entering B is 150 million standard cubic feet per day. Now from A to B is 25 miles. Since B is 25 mile post, now C is 70 mile post. So that means 25 plus 45 will give you 70. So yeah, the length of this of BC will just be 45 mile post. Now we now have at D, milepost 90, gas entered the pipeline at 40 million standard cubic feet per day. So now the next point of call is D. Now they said at D you have 90, milepost 90. So this is 70 plus 20 will give you 90. Now we have the next. All streams of gas are okay to assume so. Okay, now the total length of the natural gas pipeline is 100. So from D to the delivery point, to this delivery point E, the terminal point. So here will now be 10 miles. So if you add the whole of this will give you 100 miles. At D, you can say gas entered the pipeline. So at D, gas entered the pipeline. meaning that gas enter the pipeline, which is 40 million standard cubic feet per day. Now, at A, now it enters is 150 million standard cubic feet per day. So now, if you're taking off 60, that means what will be going this way will now be 90 million standard cubic feet per day. Now, taking out 50, it will now remain here 40. So this will be 40 million standard cubic feet per day. Now, since 40 is coming in, 40 is going into this point, that means the one terminating here at E will now be 80 million standard cubic feet per day. So now, this is how the diagram will look like. Now we are given, look at the parameters we're given. We're given the pipeline to be MPS 18 and 0.375 thickness, wall thickness. We are also given the specific gravity of 0.6 and the viscosity of 7.5 times 10 raised to power minus 6 times 10 raised to power minus 6. So now let's write down. So that means our D is 18 inches and our wall thickness is 0.375 inches. Now let's calculate D, which is internal diameter, which is equal to D minus 2 times T times the wall thickness. So we have 18 minus 2 times 0.375. So this will give us 18 minus 0.75. So this will give us 17.25 inches. So D is equal to 17.25 inches. Now, we are given gas gravity 0.6, E 200 micro inch. Then we are also given the viscosity to be 7.5 times 10 raised to power minus 6 pounds per feet seconds. Now here, the base temperature, the base pressure, sorry, is 14.7 psi. The base temperature is 60 degrees Fahrenheit, which is 520 degrees Fahrenheit, is equal to, now we also have the gas temperature to be 80 degrees Fahrenheit, which is equal to 460 plus 80, which is 540 degree Rankine. Now we are asked to make use of the Z factor of 0.88 throughout the piping system. Now, question A Let's look at the question A. The question A is, it say, using the modified Colibres equation, calculate the pressure along the pipeline at point A, B, C, and D for a minimum delivery pressure of 400 psig at the terminus A. So if you look at this now, look at the question now. All stream of gas can be assumed to have a specific gravity of 0.6 and a viscosity of 7.5 times 10 raised to the power 6 pounds per feet seconds. The pipe is internally coated such that the absolute roughness is 200 micro-inch. Assume a constant gas flow temperature of 80 degrees Fahrenheit and a base temperature and a base pressure and a base temperature of 14.7 psig and 60 degrees Fahrenheit respectively, using a constant compressibility factor of 0.88 throughout. Neglect the elevation difference along the pipeline. So that is where this comes in. So now we at A, question A. Based on this, we have there given the pressure at P at E. So the delivery pressure PE is 400 psig, which is 414.7 psi. Sorry. Now let's now begin. We start from DE. We transfer from section DE. From section DE, we're looking for D now. So from section DE, the flow rate there is 18. So we now use, but before we use this flow equation, we need to calculate our transmission factor. So to calculate the transmission factor, we are going to use the modified Colibres-White equation. So where the transmission factor will be equal to minus 4 log base 10 E divided by 3.7 divided by D plus 1.425 F divided by Reynolds number. Now let's calculate first the Reynolds number. The Reynolds number is equal to 0.0004778 times base pressure divided by base temperature times G, the gas gravity, times the flow divided by the viscosity divided by internal diameter. Now let's impute our values. Now we have 0.0004778 times the base pressure is 14.7 divided by the base temperature is 520 times G, which is 0.6, times the flow rate. The flow rate of that is 80 times 10 raised to the power 6 divided by the viscosity, which is 7.5 times 10 raised to the power minus 6. Then D is 17.25 internal diameter. So what is our Reynolds number? So let's now make use of our calculator to calculate it. Now we have 0.000 4778 times 14.7 divided by 520 times 0.6 times 80 times 10 raised to power 6 divided by 7.5 times 10 raised to power minus 6 divided by 17.25 divided by 17.25. So what I'm going to get here, what I got was 5,511,307. So this is our Reynolds number. So since we have calculated the Reynolds number, we're going to make use of it in this equation to get our F. Now F is equal to minus 4 log to base 10. E is what? 200 times 10 raised to power minus 6 divided by 3.7 times 3.7 divided by 7.25 plus 1.425 times F divided by Reynolds number, which is 5,011,307. Now let's assume F is equal to 20. Let's assume F is equal to 20. So the new F will now be equal to minus 4 log to base 10, 200 times 10 raised to power minus 6 divided by 3.7 divided by 17.25 plus 1.425 times 20 divided by 5,011,307. Now let's calculate. Let's punch our calculator. Let's make use of our calculator. Now we have minus. So we have minus 4 times log base 10 bracket open 200 exponential minus 6, 200 times 10 raised to minus 6 divided by 3.7 divided by 17.25 plus 1.425 times 20 divided by 5,011,307. So what we got here is 20.218. Now we have 20.218, so close by. Now let's assume F to be equal to what? 20.218. So now let's calculate again. So we have f now to be equal to minus 4 log to base 10 bracket open 200 times 10 raised to power minus 6 divided by 3.7 divided by 17.25 plus 1.425 times 20.218 divided by 5,011,307. So let's also calculate this and see what it gives us. Now we'll say minus 4 times log minus 4 times log to base 10 bracket open 200 times 10 raised to power minus 6 divided by 3.7 divided by 17.25 plus 1.425 plus 1.425 times 20.218 divided by 5,011,307. So we have 20.206. 20.206. We have 20.206. Now let's also assume f to be 20.206. Now let's look for f now, the new value of f. So we have minus 4 log base 10 bracket open 200 times 10 raised to power minus 6 divided by 3.7 divided by 17.25 plus 1.425 times 20.206 divided by 5,011,307. So what would be our f now? We have minus 4 log times log bracket open 200 times 10 raised to power minus 6 divided by 3.7 divided by 17.25 plus 1.425 times 20.206 divided by 5,011,307. So 20.206. So final answer. So we have 20.206. So this is our final answer. So f is equal to 20.206. So since this f is equal to the assumed value, so this is where we stop. Now we have gotten the transmission factor. So having gotten the transmission factor, we now make use of it to calculate our values. Now we know that the flow rate, that is using the general flow equation, we know that the flow rate is equal to 38.77 F times the base temperature divided by the base pressure times P, or let me say PD square minus PE square, all divided by G TF LZ, all raised to power 0.5 times D raised to power 2.5. So let's work it out. So now we have 80 times 10 raised to power 6 equal to 38.77 times F, which is 20.206 times T. T is what? T is 520 divided by the base pressure, which is 14.7 times. You have PD, we're looking for PD square minus E square is 414.7 square divided by G, which is gas gravity, 0.6 divided by gas temperature, which is 540, divided by the total length of DE. The total length of DE is what? 10 miles. That length of D is 10 what? 10 miles times 0.88. That is what they say we should use throughout. That is the compressibility factor raised to power 0.5 times D, which is what? 17.25 raised to power 2.5. Now, to get LP, we need to solve for the whole of this. So that means, let me say P raised to power D square minus 414.7 square divided by okay, let me go to next page. PD square minus 414.7 square divided by 0.6 divided by 540 divided by 10 divided by 0.88 all raised to power 0.5 is equal to, now we say to make this the subject of formula, we have to move the whole of this to this side, all of this to this side. So to do that, we are going to say 80 times 10 raised to power 6 times 14.7 times 14.7 divided by 38.7, 38.77 divided by 20.206 divided by 520 divided by 17.25 raised to power 2.5. Now, to simplify this expression on the left hand side further, we Square both sides of the equation. What we do is square both sides of the equation. To square both sides of the equation, you now have p subscript d raised to power 2 minus 414.7 square divided by 0.6 times, divided by 540 divided by 10 divided by 0.88 equal to 80 times 0 is power 6 times 14.7 divided by 38.77 divided by 20.206 divided by 520 divided by 17.25 raised to power 2.5 all square. So P D square will now be equal to 414.7 square plus 0.6 times 540 times 0.88 times bracket open 80 times 10 raised to power 6 times 14.7 divided by, that's 8.77 divided by 20.206 divided by 520 divided by 17.25 raised to power 2.5 all square. Now let's calculate our D. Now let's make use of our calculator. Now we have 414.7 square plus 0.6 times 540 times 0.88 times bracket open 80 times 10 raised to power 6 times 14.7 divided by 38.77 divided by 20.206 divided by 520 divided by 17.25 raised to power 2.5. So equal to this. Now we'll now check the square root of this value. You have so let me recalculate. It's like you have 414.7 square plus 0.6 times 540 times 0.88 times bracket open 80 times 10 raised to power 6 times 14.7 divided by 38.77 divided by 20.206 divided by 520 divided by 520 divided by 17.25 raised to power 2.5 bracket close, bracket close, all squared equal to this. So now find the square root of this. So we have the pressure at D, we have 416. 416.6 pxi A. I will say 417 psi A. The increase is very small. So we have calculated the pressure at D. Now to calculate the pressure at C, calculate the pressure at C. Now we need to also calculate the transmission factor between CD. Now, but before we do that, we need to calculate the Reynolds number between CD. So Reynolds number is equal to 0.004778 times 10 raised to power times the base temperature divided by the base pressure times the okay, no. The Reynolds number is the base pressure divided by base temperature times the gas gravity times the flow rate divided by Reynolds number divided by D. So we have 0.004778 times the base pressure is 520 divided by the base temperature. The base temperature is the base pressure is 14. Sorry, the base pressure is 14.7. The base temperature is 520 times G is 0.6 times the flow rates at CD. CD is 40 million standard cubic feet. So we're using 40 times 10 raised to power 6 divided by 7.5 times 10 raised to power minus 6 divided by 17.25. Now let's calculate this. We have 0.4778 times 14.7 divided by 520 times 0.6 times 40 times 10 raised to power 6 divided by 7.5 times 10 raised to power minus 6 divided by 17.25 equal to so we have 2. So what we have is 2,505,654. So this is the Reynolds number here. Now, since we've gotten this Reynolds number, so what next? What we do next, we calculate the flow. So the flow, the transmission factor, which will now be F equal to -4 log to base 10 E, which is 200 times 10 raised to power -6 divided by 3.7 divided by D, which is 17.25 plus 1.425 times. Let's assume the transmission factor is 20 divided by the Reynolds number, which is 2505654. So our new F will now be what? So our new F will now be, say, -4 times log log to base 10 bracket open 200 times 10 raised to power -6 divided by 3.7 divided by 17.25 plus 1.425 times 20 divided by 2505654. So what we have here is 19.354. So now that means our assumed value will now be 19 point. So we now assume F to be 19.354. Now let's calculate the new value of F to see if it's the same. For -4 log to base 10 200 times 6 divided by 3.7 divided by 17.25 plus 1.425 times times should now be 19.354 divided by the Reynolds number is 2505654. Now the final value, the transmission factor, the new transmission factor will now be -4 times log to base 10 bracket open 200 times 10 raised to power -6 divided by 3.7 divided by 17.25 17.25 plus 1.425 times 19.354 divided by 2505654. So we have 19. We have here 19.398. 19.398. So we have 19.398. Now let's assume F now is what? 19.398. So F will now be minus 4 log to base 10, 200 times 10 raised to power minus 6 divided by 3.7 divided by 17.25 plus 1.425 times 19.398 divided by 2505654 equal to, so we have minus 4 log bracket open 200 times 10 raised to power minus 6 divided by 17.25 plus 1.425 times 19.398 divided by 2505654. 19.395. So we have now 19.395. So this is the final answer. Since the difference between this value and this value is not much, so that's what we're going to use. So now we're going to invoke the general flow equation, which is Q, which is the flow rate equal to 38.77 times F times the base temperature divided by the base pressure times, now we're looking for pressure, saying P subscript C square minus P subscript D square divided by GTFZ, L is the length, times Z all raised to power 0.5 times D raised to power 2.5. Now we're looking for C. We're looking for C. Now let's make this the subject of formula first. You have P C square minus P D square divided by G T F L Z all raised to power 0.5 is equal to Q times P B times PB divided by 38.77 divided by F divided by TB divided by D raised to power 2.5. So this whole is equal to this. So now let's go to the next one. Now simplifying this further, I will now square both sides. If I square both sides of the equation, we have what left? We now have PC square minus PD square divided by G TFLZ equal to Q times PB divided by 38.77F divided by TB divided by D raised to power 2.5 all square. Now PC square will now be PB square plus GTFLZ times Q times PB divided by 38.77F times TB times D raised to power 2.5 all squared. So now to get our PC, you now take the square root of the whole of this. So taking the square root of this and the square root of the whole of this will give us PC. So PC, well, let's calculate our PC now. Say square root PD. What did we get as PD? We have our PD to be 417. So 417 square plus G 0.6 times TF gas temperature is 540 times the length of this CD is what? Let's look at the length of CD. The length of CD is 20 miles. So we're going to use 20 miles. 20 miles. So 20 miles times 0.88 gas gravity brackets the flow rate. The volume flow rate is 40 times 10 raised to power 6 standard cubic feet per day times the base pressure is 14.7 divided by 38.77 divided by, we have our F to be 19.395 divided by the base temperature 520 divided by 17.25 raised to power 2.5 all squared. So let's now calculate our P. C will be equal to what? So now let's use our calculator to do this. 417 square plus 0.6 times 540 times 20 times 0.88 times bracket open 40 times 10 raised to power 6 times 14.7 divided by 38.77 divided by 19.395. 19.395 divided by 520 divided by 17.25 raised to power 2.5 brackets. Okay, brackets close, all raised to power 2 equal to this. Now we'll now take the square root of that value equal to what? 427. 427. So the pressure P C is 427 pxia. So since we have got calculated our C, we stop here. Now we continue. No, now this will be our part 1. So we continue in the next lecture, part 2. So let's stop. Let's end the lecture here. So now we continue in the next part, which is part 2. So thank you for watching to the end. Have a nice day. Also do well to subscribe to my channel, so when I make new video, you'll be the first to watch. Thank you and God bless. Now let's end the video here.